Hi, everybody. My name is Milan Ćurčić, and this talk is titled Laboratory Measurements of Air-Sea Drag and Waves in Extreme Wind Conditions. And this is teamwork with Payson Tan, who is a PhD student in our lab, Bran House, who is the lead PI on the project, and our collaborator, Pierre Sochalat, from the French Geological Survey. I'll start with a definition of the air-sea surface drag. It's the vertical flux of momentum between atmosphere and ocean. It's largely wave dependent, and it's very difficult to measure in extreme weather, such as hurricanes. And it's also an essential part of weather and ocean prediction models. Here on the right-hand side, you see a photograph of the ocean sea surface taken from an aircraft in Hurricane Isabel in 2003. The specific photo is from tropical storm force winds. And what you see are large waves that are breaking. They're white capping, so that's the foam that's being generated when a wave breaks. The air bubbles are also being entrained under the surface. And when waves break, spray is being ejected and also carried by the wind. So you see streaks. Also, that's some of the spray that's being carried by the wind. And the spray is generally suspended in the surface layer and the lower boundary layer. And that's why the visibility decreases going out. We're generally guided by three key questions. And that is, can we measure air-sea drag and hurricane winds? What are the physical processes that govern the drag? And can we better resolve it in models to improve hurricane structure and intensity prediction? In early 2000s, both from field and laboratory, there was a new finding about the drag coefficient saturation in high winds at about category 1 hurricane force winds. So here, this left panel is from Powell et al. 2003. They analyzed a large number of GPS drop zones from aircraft reconnaissance missions and used a log profile to infer the drag coefficient and found that it saturates in high winds and perhaps even decreases as we go toward about 50 meters per second U10. So the drag coefficient is just, it's a convenient diagnostic that relates the stress or the vertical flux of horizontal momentum with the wind speed squared. On the right is a figure from Donlan et al. 2004. So they did eddy covariance and momentum budget estimates of stress and drag coefficient, low to moderate to high winds, and they found saturation at about 33 meters per second U10. And this was a high impact result because it was soon after implemented in weather and ocean prediction models in the surface layer parameterization. Now, why does drag saturate in strong winds? There are a few different hypotheses. The leading ones are the sheltering and flow separation. So these are PIV images of airflow over increasingly steeper waves by Buckley and Veron from 2016. And here you see that the steeper the wave, you have more of this stagnant air immediately following a breaking wave crest. And the high-speed flow separates from the surface. And the hypothesis is that in high enough wind and steep enough waves, the flow skips from crest to crest and doesn't re-enter the troughs. Also called Tuisen et al. In 2012, they hypothesized that high concentration of streaks and not the white caps is what leads to a general what they call a whiteout, when you have an overall a lot of spray and streaks in the surface layer. And once that saturates, that may lead to a saturation or a decrease in drag coefficient. These are also based on, so the drag is based on the drop zone data, and the streaks were based on analysis of photographs from reconnaissance missions. And there's also the so-called sandwich layer hypothesis by Barnblatt et al. 2005, which basically says that when waves break, spray is being ejected and suspended in the surface layer, and that can dampen the small-scale turbulence. So we went on and we went to analyze stress and waves in the ACIST laboratory. This is the same wind wave tank that Donald and Al did in 2004. So we were basically at the beginning of this project. We were redoing their experiment, but now with more instruments, improved instruments. So our first goal was to try to reproduce the result before we move on to a larger wind wave tank. This is just the setup of the experiment. I won't go into much detail about it, but basically we did eddy covariance and momentum budget estimates of drag, and on the bottom is a photograph of the tank in action. And these were our results. So the red markers are all our measurements from SUSTAIN. Yellow are field data by Edson et al. 2013. They went into Core 3.5 algorithm, and they give a good estimate in low to moderate winds. But in high winds, there's fewer data. The original Donald et al. 2004 data is in black, and the cyan triangles are by Takagaki et al. 2012. So you see that we were able to find evidence of the drag saturation at about 25 meter per second winds. And during this analysis, we also found an error in the original source code that was used to process the drag by Donald et al. 2004. The correction is relatively simple, but once you apply it, it actually moves the data up in the drag coefficient magnitude and to the left in U10 magnitude. So it gives you a bit better agreement with the field data, which is what we expect. And this is all described in our paper from earlier in 2020. You can go ahead and read it after this talk. Now we're moving on to our more recent results from the SUSTAIN wind wave tank. These are just a few photos from above the tank, inside the tank while setting up the instrumentation, under the tank, and what it looks like from the side once we're running it in high winds. So we took a few different measurements. We have eddy covariance stress from a sonic anemometer that's pictured on the right at 3 different fetches, 7, 9.5, and 12 meters. So fetch is the distance in the tank from the inlet. And we also have eddy covariance stress from a hot film anemometer at fetch 9.5 meters. So hot film anemometer is this very tiny instrument. The sensor head are 2 tiny wires about 1 millimeter apart, and it measures at 1,000 hertz, so very high frequency, horizontal and vertical velocity, from which we can calculate eddy covariance stress to high reliability. And we also have wave measurements at various fetches. Oh, actually, here I have a video to show you what it looks like in the tank across various wind speeds. So this is a view from the side. And here U10, so wind scale to 10 meters is shown in the left. As the wind increases, we have more and more breaking waves, spray generation. These conditions are very violent, but in the lab, we have the control to take robust measurements in such conditions. I'll let it play just one more time and then move on with my slides. Okay, so just to give you an idea of what the waves look like in the tank and how they develop. Here, each panel is a spectrum of waves. So that's a distribution of wave energy by frequency. So on the left are long waves, on the right are shorter waves. And the peak here in low winds is about, that's 3 hertz. And as we increase the wind, the wind speed peak moves down frequency, so it goes toward longer and longer waves. The peak also broadens, so that we expect from the wave dissipation and also nonlinear wave interactions. So this is what the spectrum in the end looks like. This is inside the tank, 43 meter per second wind. And finally, we get to our new drag coefficient measurements. Here we're showing just the lab data, but in red are our old ACEST data, or quote unquote old, the ones that I showed just earlier, from 3 different methods: hot film and sonic anemometer eddy covariance, and stars are the momentum budget, and the magenta markers are new measurements. So we haven't yet processed the momentum budget calculation, but we have eddy covariance from hot film and sonic, which give us pretty good confidence about these runs. And also you see multiple markers here in each group. They're just multiple runs that we did, just so that we're confident we can reproduce the results. And in general, you see increase with wind, and at about 25 to 30 meters per second, there's a decrease in the slope. So there's definitely saturation, although we find that it's not at a constant value, but it has a very gentle slope. To compare with the field data in low to moderate winds, so this is our ground truth. So this gives us confidence that we have good magnitude of drag in low to moderate winds. Out here, there's no direct data from the field, but there is data in high winds from indirect measurements. So Powell and Holtuisen, which I mentioned earlier, the triangles and circles, they're from GPS dropsondes. And then Jarosz and Shu et al., which are based on ocean momentum budget. Jarosz is based on ADCP data in Hurricane Ivan, and Shu et al. Are based on EM apex floats from several typhoons. But overall, you see that these GPS dropsonde and ocean momentum budget estimates of drag, they tend to have a very high spread. They show decrease in high winds. However, in the lab, we weren't able to find any evidence of decrease. So far, at least from these results in the lab, the drag keeps on increasing at a very gentle slope going up. So we don't have a decrease. And then we're also working toward connecting waves and stress and improving existing wind input functions. So specifically, we focus on the Jeffries 1925 sheltering hypothesis, and further refined by Donlan et al. 2012. And that basically relates wind input to be proportional to the wind speed relative to the phase speed of the moving wave, and then squared. But this is a sign preserving square. So this function works for both negative and positive momentum flux, so upward or downward. And omega and f are just wave frequency and wave spectrum. Now, in the past, this sheltering coefficient A, circled here, has been considered a constant. Several studies have tried to find it and measure it in the lab. What this constant really is, what it means physically is, here it's shown in this panel. This is a monochromatic wave, just for illustration. And this is wind flow over that wave. And you have wind entering the trough and attaching to some part of the crest of the following wave. But you have separation of the flow, meaning this part of the wave phase is sheltered. It's not directly forced by the wind, whereas this part is exposed and directly forced by the wind. So the sheltering coefficient A is the proportion of the exposed area to the wind forcing. This gives us form drag as an integral of the wind input function of their spectrum. And these are also the new results of the sheltering coefficient from the same runs that I just showed. This is sheltering coefficient is a function of wind speed. So we have a decrease as the wind speed increases, which is what we expect. And also a decrease in mean square slope. And finally, we also quantify it as a function of the wave Reynolds number, which just it's proportional to the wind forcing, significant wave height, and air viscosity. And finally, we're starting implementing and testing new drag and sheltering parameterizations in couple modeling. We're currently working on Hurricane Dorian, and we also plan to simulate other recent major Atlantic hurricanes. And we're also working on a stochastic drag parameterization for WRF with Pierre. And now I'm going to show you just a video of this so that you can see so this is wind speed during Dorian landfall at Bahamas. And on the right, you see how SST decreases in the wake of the storm due to strong wind forcing. And finally, these are my takeaways. We got new drag coefficient data from the SUSTAIN laboratory. It provides further evidence of drag saturation. However, it does not appear to saturate at a constant value. It has a gentle slope. We find no evidence of drag coefficient decrease in high winds. And we also have collocated stress and wave spectrum measurements, which help us quantify sheltering in a variety of conditions. And we're working to implement and test these parameterizations in coupled modeling of real tropical cyclones. Thank you very much, and I look forward to your questions. Have a great day.